Hello, and welcome to the Getting Started with the Yocto Project screencast. This screencast is intended to provide a gentle introduction to the Yocto project from a developer's perspective. You don't need to have any prior experience with the Yocto project to follow along with this screencast, but you will find it helpful to have some prior experience working with Linux systems, and having a basic understanding of how software is configured and built under Linux. My name is Scott Garman, and over the next half hour, we're going to walk you through a couple of builds of an entire Linux OS and show you some of what's going on behind the scenes. While there's no way we can cover everything you need to know with this screencast, the goal is to get you familiar enough with the build system that you can get the most out of our documentation and to start your exploration of the Yocto project with a solid foundation of knowledge. So we'll begin by spending a couple of minutes examining the goals and benefits of the Yocto project, and then give a high-level overview of Yocto's build system. We'll take a closer look at recipes, which are an important, fundamental part of the build system, and then we'll actually build and run a Linux image under emulation. After that, we'll discuss Yocto's layering system and how board support packages are used as layers. And finally, we'll see how easy it is to rebuild a Linux image for a different board, and I'll point you to some useful project resources for further research. So the purpose of the Yocto project is to help you build a custom Linux OS for just about any kind of embedded computing device. Yocto can create Linux images for all the major hardware architectures, including x86, ARM, MIPS, and PowerPC. Yocto is essentially an umbrella project where the open source community and industry is coming together to collaborate on a set of tools and best practices for developing custom Linux images. The idea is not that this is a Linux distribution which sets software policies that ultimately get in the way when developing our products. Instead, Yocto is focused on enabling a high degree of flexibility and customization, which is critical when you're developing Linux-based embedded products and you need to have a great amount of control over the software running on your device. Whether you need to focus on getting your device to boot up as quickly as possible or enabling certain optimizations in your software, Yocto allows you to do this while adhering to practices which allow you to reuse your software stack across a wide range of hardware platforms, saving your organization time and money. The Yocto project is hosted by the Linux Foundation, making it a project independent of any particular company or vendor. But as an open source project, many companies and individuals are shaping the future of the project through their involvement and code contributions. As you can see, there are quite a few organizations backing the Yocto project. They range from silicon vendors to OSVs to consulting groups. And if you'd like to become an official participating organization, we encourage you to do so. Please contact the Linux Foundation for details. There are many benefits to be gained from adopting the Yocto project. One of the most important of these is being able to reuse your development efforts, regardless of the hardware device you're working with. No longer will you have to retool your development processes every time you begin using a new embedded board. With the Yocto board support package, often all that's necessary to rebuild your software for a new platform is to change one line in a configuration file. We'll be demonstrating this later in this screencast. Yocto gets you started with a validated set of software applications and libraries, and since we're based on Open Embedded, there are thousands of additional recipes that you can easily port to Yocto. Yocto offers integration with a great set of developer tools, such as an Eclipse plugin for application development, as well as tools for debugging and profiling, analyzing power consumption, and more. Finally, the fact that Yocto is an open source project allows you to get started working with it immediately. You can use it to develop prototypes or fully finished products. Should you decide that you want commercial support, any of the OSVs listed on the previous slide can provide it, without forcing you to adopt a completely different build system. So now that you've learned a few things about the Yocto project, let's turn our attention to the build system. The name of the build system software that Yocto uses is called Pocky, and Pocky consists of two major components. There's bitbake, which executes and manages all of the build steps, and a set of metadata, which describes what gets built and how to build it. The metadata is broken down into three main types. We have configuration files, which define global defaults for things such as standard file system paths where the build output is to be placed, compiler flags, machine architectures, and so on. There are bitbake classes, which end in the .bb class file name extension. And these are what really do most of the heavy lifting in the build system. For example, we have bitbake classes which define how you build a Linux kernel, or how you build an AutoTools-based piece of software. We have ones for how to generate an RPM package, how to create a root file system image, and so on. Finally, there are recipes, and recipes define an individual piece of software to be built. So we have a recipe for the GNU tar command, a recipe for the GTK library, and so on. Recipes are also used to define what packages get included in your final file system image. So one of the key things about Yocto is that it provides a very flexible set of tools to create highly customized Linux images that are tailored for the embedded device that you're using. It gives you a great deal of control over what software and features you want to include in your image, but at the same time it offers a sensible set of defaults to begin with when you're getting started developing your embedded product. The building blocks of these images are recipes, and we'll be taking a look at some recipes very soon. But I want to make clear from the start that a recipe is not an entire script or makefile which builds a software, like it is in some other build systems. Instead, recipes include bits of metadata about the software, such as where you download the upstream sources from, build or runtime dependencies, and what features you want enabled in your application. You can also split up the final output of a recipe into multiple binary packages. For example, you probably want to separate out the documentation files into another package so that you can choose whether or not to install that package into your image. In most embedded applications, you would probably leave it out to save disk space. This workflow diagram provides a high-level overview of what's going on during a Pocky build. The first step is to download the sources for the software that you're going to be building. We refer to this step as fetching the sources. We of course support standard methods such as downloading a tarball from an HTTP or an FTP site, and we also allow you to check out sources from a number of different source code repository systems, such as Git or Subversion. Once the sources have been downloaded, they will be extracted into a local working area, where any necessary patches will be applied. At that point, the common steps for configuring and compiling the software will be run. The software will then be installed into a temporary staging area, at which point the binary package format you've selected will be used to roll up the software into one or more output packages. During this process, there are a number of different QA and sanity checks that get run, such as checking to ensure that the software just built wasn't linked to software libraries located outside of the build system. It's actually not true to say that all of these tests get run in one step. There are many different checks that are run throughout the entire build process. Once all of the needed binary packages have been created, a binary package feed is generated, which then gets used to create the final root file system image. The fact that a package feed is used in this process becomes very useful if you're developing an embedded product with networking capabilities that may need to be updated in the field. What this allows you to do is to copy that package feed onto a network server and then design your online updating system to pull its updates from that package feed. When you do this, you can take full advantage of the package management system you're using to do things such as automatically resolve package dependencies and make sure that your update packages get installed in the correct order. Finally, you'll notice that the file system image and application development SDK are generated in parallel. It's true that there's not one single SDK that you can use to develop for any Yocto-based embedded device. That's because Yocto isn't a Linux distribution, and instead allows you to decide what software and libraries get included in your Linux image. So when you generate your custom Linux image, you can also generate an SDK which is custom tailored for the software you've chosen for your Linux image. So in a nutshell, this is what happens during a Pocky build. Since we're building everything from source, a side effect of this process is that the first build you run can take a significant amount of time. The good news is that we've developed various caching mechanisms to speed up successive builds. The sources you've downloaded, for example, are kept in a separate area and will not be re-downloaded each time. Also, we maintain a cache of the binary build output that gets generated, so you're not going to be recompiling the same software over and over when running successive builds. Only if you make changes to recipes will those parts of the system get rebuilt. Now, there was a lot to cover in that last slide, but in contrast with the amount of work that Pocky goes through to generate an image, we've tried to make it extremely easy to get started building your first Linux image with Yocto. It literally involves just a handful of commands, and a bit of patience during your first build while it completes. Please follow our Quick Start Guide in the documentation section of the yoctoproject.org website to install the necessary build system prerequisites on your Linux system. Then you should be able to follow along with the live examples I'll be showcasing during the remainder of this screencast. So now that you have some background information about the Yocto project and an abstract understanding of the build system's workflow, let's take a look at some more specific things. For this exercise, we're going to take a look at the source tree you get when you download Pocky, and I'll show you where different types of metadata are kept. The Linux system I'm using for my build host is based on Fedora 16. I generally recommend using a recent release of Fedora, Ubuntu, or OpenSUSE for your build host, since those three Linux distributions are the ones we do most of our testing on. Now, in theory, you could run builds from within a virtual machine, but if you can avoid it, I don't recommend using one for performance reasons. If you do end up using a virtual machine for your builds, please keep in mind that builds will take much longer, typically 2 to 3 times as long than if you were running Linux natively. So I'm going to start up the graphical file manager here to browse the Pocky sources. You can see that the tarball release of Pocky 6.0 has already been downloaded and extracted. Within this directory, you'll find several subdirectories. The bitbake directory is where the bitbake command and sources are kept. I'll come back to the build directory in just a second. The documentation directory is where we keep the sources to our documentation, and you'll find them easier to read just by simply going over to the documentation section of our website at yoctoproject.org. And you'll notice that we have a number of meta directories. These are where the main metadata files of the build system are located. And the reason that we have multiple directories is that each of these directories represents a layer, which is a concept we'll be diving into later on in this screencast. Within the meta directory, you'll notice that we have recipe subdirectories where we store the recipe files. Here's where you'll find our recipe files for the BusyBox environment, for example. Under the classes directory, you'll find all of our bitbake classes. You can see we have classes for AutoTools, for the CMake build system, and the one here for cpan would be used for building Perl modules, and so on. Under the conf directory, you'll find different kinds of configuration files for the build system. One of the top-level configuration files is bitbake.conf, which, as you can see here, defines default file system paths and sets up architecture-specific build variables, and quite a bit more. In the machine subdirectory, we have machine configuration files, which define hardware characteristics of our QEMU targets. Note the require lines here will pull in the contents of additional files. Going back up to the top-level directory, the scripts directory contains a number of support scripts that the build system uses. For example, we have some scripts in here to help simplify running the QEMU emulator. Now, the build directory is something which gets dynamically generated during builds, and under here is where all of your generated output is stored. The downloads directory is where all the upstream sources get downloaded to. State cache is where we store compiled output that can be reused during successive builds. And the temp directory is where the builds are performed. You'll find the work directories under here, as well as the sysroot directories, and so on. The conf directory is very important as it stores your local.conf and bblayers.conf files, which set up critical variables that you'll want to take a look at. Local.conf, for instance, allows you to set up things like how many threads you want bitbake to use, what target machine you're building for, what packaging format you want to use, and so on. The bblayers.conf file specifies what metadata layers you want to make use of. Since a board support package is distributed as a yocto layer, you'll no doubt want to enable that within your bblayers.conf file. So that's just a quick walkthrough of the Pocky directory tree to give you a bit of the lay of the land. Why don't we build our first image? Open up a terminal and cd into the Pocky directory. Now we're going to source a script called oe-init build env. This script simply sets up some basic environment variables and automatically changes your working directory into the build directory. Before starting the build for the first time, you always want to open your local.conf file and make sure you've specified the desired target machine, as well as set the performance-related variables to get the most out of your build hardware. In this case, I've set the target machine to QEMU x86, and the parallelism options to 2 and 4, which is appropriate for my dual-core laptop. For a quad-core system, I'd set these to 4 and 8 instead. Now that we've done that, we want to make sure we're in the build subdirectory, and then we run bitbake core image minimal. This kicks off the build, and now it should just be a waiting game. To give you an idea of what you should expect at this point, if you have a modern quad-core i7 processor and 8 GB of RAM, this build should take about an hour and a half if you're running it on native hardware. Keep in mind you're building an entire Linux operating system from the ground up, and if you're running this on a virtual machine, it's going to take even longer than that. With our build running in the background, let's take a closer look at recipe files. This slide shows an example recipe for the ethtool utility. As you can see, we specify some metadata about the purpose of the software this recipe builds in the summary, description, and homepage fields. We also specify the license or licenses that the software is distributed under. Most importantly, we use the source URI variable to tell bitbake where to download the upstream sources from. In this case, we are downloading it from SourceForge. The PV variable in the source URI stands for the package version, and it corresponds to the portion of the recipe file name after the underscore. In this case, it expands to 2.6.36. Doing this makes it easier to upgrade this recipe when a new version of ethtool is released. It allows us to simply rename the recipe file and minimize the set of changes that we need to make to the contents of the recipe. Finally, you'll notice the inherit autotools line. This line tells bitbake to use the autotools.bb class logic to build this software. By making use of these bitbake class files, you can keep a great deal of complexity out of individual recipe files. This is a design goal of the Pocky build system. Since we have so many individual recipe files, we try to keep them as simple as possible, and take care of the build logic within bitbake class files instead. The process of building a piece of software, no matter what kind of build system it uses, comes down to a set of standard steps that we run with bitbake. These steps are listed here, and include fetching the sources, unpacking the sources into the work directory, patching the sources, configuring the sources, compiling them, installing the compiled output into a staging area, and packaging the output into one or more binary package formats. What's happening behind the scenes when you inherit something like autotools.bb class is you're inheriting a version of these build steps that works to correctly build the software using the desired build system. In addition to this, you can further override these build steps by defining them within your recipe file. We'll see some examples of this shortly. Now let's take a closer look at some specific recipes. The first one we'll check out is Minicom, which is located under Meta, Recipes Extended, Minicom. And you'll recognize the same kinds of metadata that we saw in the ethtool recipe example slide. One new field to take note of is the depends variable. This variable is used to declare any build time dependencies. So in this case, we're saying Minicom depends on the ncurses library, so bitbake will make sure to build ncurses first. We also have a license files checksum field, which we use for tracking potential changes to licensing information from the upstream sources. This works by specifying one or more files that include license information and taking the MD5 sum of that file. Should the file change in a future release of the software, bitbake will warn us about a checksum mismatch, and we can stop to inspect what the changes actually are in order to verify whether the license has changed. We can do this with entire files, as with the copying file here, or with just a section of the file, which we're doing here with a minicom.h file, only checking the first 12 lines of the file, which presumably has some licensing info. For the source URI, we can see that we're downloading a tarball from a debian.org website. But we also include an additional line here, which references a patch file. You may be wondering where these patches are kept. So if we go back to our file browser, we're in the Recipes Extended Minicom directory. And in addition to the recipe file itself, you'll notice that there's another directory named after the recipe's file name. And if we look in here, we'll find the patch file. You can store patches in this directory as well as other files that your recipe might need, such as custom init scripts. Going back to the recipe, we have some additional fields associated with the source URI. These are the MD5 and SHA-256 hashes of the source tarball. We do this to make sure that the upstream sources haven't been tampered with or corrupted due to a bad download, since those hashes should not change for this particular release of Minicom. You'll see here that we're inheriting not only AutoTools, but also the getText bitbake class. getText is used to manage localization support during the software build process. And finally, we see that a doInstall function has been defined. And so this means instead of using the doInstall function defined in the AutoTools bitbake class, we're running the contents of this function instead. This is an important feature we provide because not all software follows the exact same build pattern, even if it is using AutoTools. So this gives us the control to override the behavior of any build step when necessary. Another recipe we can look at is the readline recipe, which is located under Recipes Core Readline. This, of course, is for the GNU readline library. And so we start with the typical boilerplate metadata at the top, and you'll notice that readline also depends on the ncurses library in order to build. We also have a couple of patches that we make to readline's build system. You'll notice that we've defined a couple of functions, but in this case the doConfigure function has an underscore prepend at the end of it. And this is a hook function that allows us to run the contents of this function before the doConfigure step is run, instead of overriding it completely. Likewise, we have an underscore append hook function for doInstall, so the contents of this function will be run after the doInstall step. Finally, you'll notice the bb class extend variable. This allows us to create virtual versions of this recipe to exist for the native and native SDK cases. Native recipes generate software which is not installed on the machine target, but is used to bootstrap the build system so that the target software can be built. This is typically done for utilities that need to run on the build system, such as Quilt Native, which we use to apply patches. For our final recipe example, let's take a look at the psplash recipe. psplash is a system for displaying a graphical splash screen logo when a system is booting up. It's kept in Recipes Core psplash. And you'll notice that this recipe, instead of a version number at the end of the file name, has the word git instead. As you might guess, this means that the recipe pulls its sources from a Git repository. The Git repository is specified in the source URI, as you can see here. And by default, this will pull the latest version from the Git repository every time psplash is built. To specify a particular commit to build from, you would set the commit hash in the source rev variable, as is done here. The S variable here refers to where the sources are stored within the work directory. You commonly have to set this manually when your source code doesn't get extracted like a tarball typically does into a directory whose name matches the name of its recipe and version number. We're inheriting AutoTools again. By far it's the most common build system for Linux programs. But we're also inheriting package config and update RCD. Package config is an interface for locating shared libraries that the build system of psplash uses. And update RCD means that this software is an init daemon, and so needs some logic enabled to support that. The files underscore pn variable allows you to control which files go into which binary packages. pn corresponds to the name of the recipe without the version number. So here we are manually adding the /mount.psplash file to the package named psplash. This recipe also uses the prepend hooks for the doConfigure and doInstall steps. And finally, the init script variables here need to be set when you inherit the update RCD class. They specify the name of the init script file, as well as options to set the run levels of when the init script gets run. One thing I'd like to mention is if you ever come across a variable within a recipe that you don't recognize, the first place to look for it is in the Yocto Project Reference Manual, which you can find on our website at yoctoproject.org. Once your build of Core Image Minimal has completed, we can boot the image with the QEMU emulator. The image files are generated under Build, Temp, Deploy, Images. And as you can see here, there is a kernel and a root file system in ext3 format, as well as a tarball of the root file system. Pocky includes a script called runQEMU, which automatically passes appropriate options to the QEMU command. All you have to do is run it from the build directory and pass it the name of the QEMU architecture you've built. So we'll simply invoke run QEMU x86. And as you can see, our Linux system is booting up for the first time. When you get to the login prompt, the root account by default doesn't use a password, so just hit enter and you'll be logged in. As you can see, the root file system for this image is about 12 megabytes. You can actually create a Linux image much smaller than that if you make use of our Meta Tiny layer, which is currently under development and is expected to be included with Yocto's 1.2 release. To shut down the QEMU session, simply issue the shutdown command. Let's take a few minutes to understand layers in the Yocto project. Layers are a powerful design mechanism that allow you to change out different software stacks in a modular fashion. A layer includes a set of bitbake metadata, so it can include configuration files, bitbake classes, and recipes. In the Yocto project, a board support package for a particular hardware device is distributed as a layer that you enable in your bblayers.conf file. This allows you to develop the software platform for your embedded application, and then deploy this application on any hardware platform that you can get a Yocto board support package for. You can also add support for certain classes of software, such as a particular library environment or a software tool suite, by obtaining or creating a Yocto layer for this software. This diagram shows how layers can be used to develop a fully featured embedded product. Each layer has a priority associated with it, so you can control which levels have higher priority over others. At the base of this example, we have the Open Embedded Core and Yocto metadata layers, which are included in the Pocky tarball that you download with our releases. On top of that, you would add a BSP layer for hardware support, and possibly include a layer which consists of software for a user interface or application library. Commercial Linux vendors also have an opportunity to customize and add value to Yocto-based embedded environments by maintaining their own layers. Finally, you might want to enable debugging and profiling support during the development of your application. If you create a layer which enables these features, you can develop with this layer enabled, and then disable the layer when it comes time to move your application into production. As I've mentioned, board support packages are layers whose focus is on enabling hardware features and specifying the drivers used with a particular hardware device. A typical BSP layer will include a Linux kernel configuration, specify which graphics drivers to use if appropriate, and include any other recipes, including user space ones, that are needed to enable custom hardware features. Let's walk through an example of using a layer by obtaining and enabling a board support package. Let's say that we want to build Core Image Minimal for an Intel Cedar Trail embedded board. To begin, we'd go to the Board Support Packages page on the yoctoproject.org website. This can be found under the Download tab. Make sure that the BSP you've selected is supported by the release of Pocky that you're using to build it. Since we're using Pocky 6.0, this one should work for us. The board support package is distributed as a tarball that we download. Inside this tarball, you'll find documentation files that tell you things such as how to install the image onto the embedded board, release notes, and who the maintainers of the BSP are. The base directory of the layer is the one which has the subdirectory name conf with a layer.conf file within it. So in a minute we'll be adding the meta Cedar Trail directory to our bblayers.conf file. As you can see, this layer includes a machine configuration file. Since it's named cedartrail.conf, we'll be setting the machine variable to cedartrail within our local.conf file. This BSP also includes custom recipes, which set the appropriate configuration for the kernel and X server. The binary directory that you see here is optional for BSPs, and may include pre-built reference images or kernels. Now let's enable this layer in our Pocky build system. First we edit our bblayers.conf file and include the meta cedar trail directory. Note that this must be an absolute path. Now our build system has access to all of the additional configuration files and recipes that the BSP offers. Next, we set the machine variable to cedartrail in our local.conf file. Now it's just as simple as bitbaking our desired image. The resulting image files will be generated under temp deploy images and can be copied over to the Cedar Trail board based on the documentation included with the BSP. As you can see, the layer system that the Yocto project uses allows you to look at hardware support as a simple matter of plugging in the desired layer or layers that you want to use. As the Yocto project community continues to grow, the layer ecosystem allows embedded application developers to dramatically improve time to market and reuse code more easily than ever before. Here are some final notes about the Yocto project that you should be aware of. We are an open source project with a lot of participation by the embedded community and industry, and you're welcome to dive in and contribute anytime. Our website at yoctoproject.org will get you started with documentation and other resources. We have mailing lists that you're encouraged to join, and our source code repository is at git.yoctoproject.org. Bug reports and feature requests are normally submitted via our Bugzilla site.